Hi, it's Frank Hoos from MiniLathe.com. Today I'm going to talk about the drilling capabilities of the mini mill, and you may have seen my introduction to the mini mill video, which talks about the capabilities for milling. But the mini mill is also set up in such a way that it makes a really nice miniature drill press, and particularly where very accurate positioning of holes is required, you can use the X and Y table adjustments to place the holes very accurately. And you have here on the side a 3-spoke hand wheel, much like you'd find on a drill press, but it has the ability to move the head all the way up and down the column, which is very handy, as I'll talk about a little later in the video. The spindle on this particular mini mill has what is called an R8 taper, and it's a standard taper that's found on Bridgeport style milling machines. And this is an example of an R8 taper shank here. You can see it has a slot here that mates with a pin that's actually inside of this tapered head or tapered spindle. And there's usually a little circular mark here or a hole that gives you an indication of where the pin is. And you insert your R8 shank up in there and twist it a little bit back and forth until you feel it align with that pin. And then you tighten up the draw screw here with a drawbar to lock the spindle in place, or lock the shank in place in the spindle. And that ensures that it doesn't work loose if there's any vibration involved. Once you have the shank mounted up in the spindle, you tighten this draw screw or nut that's up on the top here, up on the top of the head. And there's a wrench that comes with the mini mill that fits that. There's also a locking pin. And on this particular mini mill, it's a long locking pin that goes through the side of the head, and you have to twist this until that pops into place. And what that does is prevent the spindle from turning while you're tightening up the drawbar. So you don't need to put too much force on that, but you do want to snug it up so that it's not going to work loose. Be sure to remove the locking pin before you turn on the mill, or you could actually damage the gears inside there. Now, on some other mini mills, the locking pin actually fits into a little hole or recess here in the side of the spindle, and as you can see, it's a very short locking pin. I think in the instruction manual it's referred to as the fixing pin. But what its purpose is to fit into this hole and just give you a point of leverage that you can hold the spindle steady while you tighten the drawbar up top here. But I like this type a little better because you aren't likely to forget to leave it in place, although you could. As you can see, it will sit in there. And if you were to turn on the mill with that in place, obviously it's going to go flying off across the room somewhere. But because you have it in your hand and the hole's not very deep, that's not too likely to happen. But obviously you always want to make sure you withdraw that right away and don't ever leave it in place. Now, for our first drilling operation, I'm just going to use this piece of scrap I grabbed out of the scrap box. You can see it's already got some milling operations done on it and a slot cut in it with some sort of saw, and at least several other holes drilled in it, it looks like. But this will suffice to show just a basic drilling operation, and I think I'll use this side since it's relatively flat and clean. But in order to drill it, we want to hold it in the vise. And if I were to just put it in the vise, you can see it drops down. I could hold it up like this and attempt to tighten it up. If I can find the screw, here it is, the handle. But this piece, being kind of just a random piece, you can see is not square. When I try to tighten it up in the vise, it doesn't actually grip tightly on it. So if I were to try to drill this, and particularly if I drilled over here, it's just going to push it down like that, which obviously is not going to give us a good result. So when you're working with a piece of rough shaped material like this, you need to do something to compensate for that. Now, the first thing we want to do is do something to hold it up so it doesn't drop down. And the standard way to do that is to use a pair of what are called parallels. And these are just precision ground parallel bars that come in sets in varying heights. So you can see these here are marked 1/4, which is their thickness, by 3/4, which is the height, by 6, which is their length. And these are fairly standard ones for larger size mills like a Bridgeport. But as you can see, they're kind of longer than you need and probably longer than you want for a vise of this size that you would use on the mini mill. Now, fortunately, there are smaller sets available, and in particular, littlemachineshop.com sells some short ones like this that are only 3 inches long, and I really like them because they fit just right in this vise, which is also sold by littlemachineshop.com. So when you scale down to mini lathe type operations or mini mill type operations, you may have to look around a little bit to find suitably sized parts. But even with that in place to hold the workpiece up, we still have this other issue here of the vise not gripping tightly because the workpiece is not square, and I'll show you in just a minute how we'll fix that. Well, the standard solution to getting a rough piece to fit is to just grab a small diameter piece of wire or round stock. Some guys like to use welding rods, but I don't happen to have any because I don't do any welding. So this is just some wire I got off of something, and it's nothing precise at all about it, but what it's used for is to fit in that gap there and take up the unevenness so that we can get a firm grip on this piece. So it's now seated in there. I can tighten it up a little more, and it's locked in there pretty tightly now. And it's also seated on these parallels so that it's parallel with the base of the vise, and if the workpiece itself is parallel, then this top will also be parallel to the base of the vise. But you can't always trust that on a workpiece that you're not sure about. I happen to know that this one is pretty square, top to bottom at least. And it's good enough for this demo purpose, so we'll just leave it at that. Well, now that I have my workpiece securely clamped in the vise, the next step is going to be to use a center drill as a starter drill to drill a shallow starter hole. And this short drill here is called a combination center drill and countersink, or sometimes just called a center drill. But they're used to drill a shallow starter hole that will prevent the twist drill from wandering off of the desired locations. Twist drills, because of their length, tend to be somewhat limber, and without something to guide them in place, such as the starter hole, they can easily wander off the desired location of the hole and cause a hole that's either off center, off of the location that you want, or possibly even at an angle to the vertical. So it's good practice when doing machining work always to use a center drill to create a starter hole, and that will help to ensure that your twist drill goes through square and accurately where you want it. So we'll clamp that into the chuck. It's also a good idea to wipe the outside diameter of the drill, make sure there's no chips or grit or other foreign matter on that surface that might keep it from aligning properly. And if you've been doing a lot of work and have chips up on the chuck, you may also want to use a chip brush to clean that matter off of the drill chuck so it doesn't cause any problems. These are inexpensive brushes. They're available in the paint department at hardware stores, and you can get them from Harbor Freight and other sources. But they're generally called chip brushes. So we'll put our starter drill in there, our center drill, and tighten it down. And I like to use all 3 holes just to make sure I've got a good, even, tight grip on it. And now we're ready to do our drilling operation. Now I've decided to use a 1/4 inch diameter twist drill for our test hole, our demonstration hole. So I've selected a number 3 center drill, which is about the same diameter, maybe just a little bit larger than the 1/4 inch drill. So we'll go ahead and start up the mill. It's a little bit noisy due to the gears up here. Now, I like to use a few drops of cutting fluid. This is a product called Cap Magic Aluminum. I put it in a small dropper bottle. The cutting fluid, the Tap Magic aluminum, helps to make sure that the metal chips do not adhere to or weld to the drill bit. And aluminum in particular has a tendency to grip onto the drill bit and adhere itself, and that will cause the hole that is being drilled to be rough-edged or sometimes oversized or misshapen in various ways. So the cutting fluid does a great job in this case of helping those chips to flow freely away from the drill bit there and give you a clean hole. So you may have noticed when I drilled the hole, I did not come down all the way beyond the tapered cone part of the drill bit. So when you're using a center drill, you only want to come down about 2/3 or 3/4 of the tapered area, and you don't want to come all the way into the cylindrical profile area of it. That's going too far, because the goal here is just to get a starter hole. So now I'm ready to remove the center drill, and we'll put our twist drill in place. Now, one nice thing about the mini mill, I can raise and lower the head without losing the registration. So once the head's lined up with the hole, I can raise and lower the head as often as necessary and have confidence that the drill bit's still going to be aligned. And that is one of the things I mentioned earlier that's nice about this dovetail column, is you have quite a lot of range of movement compared to a drill press or other types of mills that have just a quill, which may only have a 2 or 3 inch range of motion. So with the mini mill you have probably closer to 6 or 7 inches, but we'll talk about that a little bit later. So let's go ahead and turn on our motor again. And there was already plenty of cutting fluid on the surface of the material here, so I didn't need to add any more. You may have noticed I started to grab those chips, not chips, but strands of aluminum, and pull them off. And that's a very bad practice to use your hand to do that, because both the edges of the drill bit are sharp, but these shards of metal can actually be razor sharp and really slice your fingers badly. So you don't ever want to grip them by hand. Often you can just knock them off with a brush, particularly if you've used cutting fluid. They will usually not adhere to the drill bit, and you can just brush them off. But if necessary, use a pair of needle nose pliers or leather gloves or something, but not your bare fingers, or you'll quickly have a bad laceration, or you might. So you don't want to do that. Now, you may have noticed I didn't say anything about the RPM or the rotational speed of the spindle to be used for that drilling operation. And the reason is it's not at all critical for this type of work, particularly considering it's a demonstration. But in general, for home shop type work, you have a lot of latitude in selecting your cutting speeds. Unlike in industry, where the goal is to remove metal as quickly as possible and balance that with a reasonable lifetime for your cutting tools. So in industry, a great deal of attention is paid to using the optimum cutting speeds for various materials and types of the hardness of the cutting tool and so forth. But for home shop, really the general rule is for larger holes you want to use a slower speed, and for smaller holes you want to use a higher speed. So if this were a 1/16 of an inch diameter drill, I might want to be running that at say 1500, 2000 RPM. For a hole like this, 700 or 800 RPM is fine, maybe up to about 1000. But I'm very lax about that in my own work and rarely have any problems as a result. Now, when you get up to half-inch diameter drills, you got to use a slower speed, obviously, and you don't want to generally try to drill a half-inch hole all at once. You want to start with a smaller diameter drill and maybe 2 or 3 and work your way up to the larger diameter hole. So if I was actually going to drill the finished hole, for example, to a half-inch diameter, I might start with a 1/4 inch diameter drill, and then I might next go to somewhat larger size. I'm just going to pick a drill bit at random here. somewhere in between the 1/4 inch and the 1/2 inch, and I can't read it because my eyes aren't very good. It looks like 11/64 maybe. But anyway, I would then choose an intermediate size drill and drill it out with that, and continue that process until I got to my 1/2 inch drill. So I might drill 2 or possibly 3 pilot holes before I get to my final diameter. I'm going to use a little smaller spindle speed this time, or a little slower spindle speed. Okay. I wanted to show you on this particular mini mill, on the side of the head here, there's a lever. It's called the high-low range lever, and it's used to shift some internal gears that are inside the head from a high range to a low range. And right now I've moved it into the high range setting. And in the high range setting, you can go up to about 2,500 RPM. So let's try that. And in the low range setting, which is where we were before, it has a range from about 0 to 1,100 RPM. Now, for most milling work, you can leave it in the low range, but the high range is useful if you're drilling or milling with a small diameter tool. For example, if you had a drill bit that was less than a 1/4 inch in diameter, you might want to go into high range. And certainly if you're getting down into the 1/8 inch diameter or 1/16 inch diameter size range of your drill bit, you want to be in the high range and use the higher RPM setting. So that's how you do that, and you may have to turn the spindle. In fact, you generally do have to turn the spindle while you're shifting this gear in order to get the gears to mesh. You can feel when it drops into place. Don't ever try to adjust this or change the setting while the motor is turned on, however, or you will damage the gears and have a significant repair job ahead of you. So always turn your mill off, and then make your setting adjustment, and then turn the mill back on. That way you'll ensure your own safety and avoid damaging the gears. Now the mill I'm demonstrating right now is the model X2D, sold by littlemachineshop.com. It's manufactured by SIEG and sold under the SIEG brand name. And it has what I like to refer to as the classic style motor, this big black motor here. It's a 350 watt DC motor, and I call it classic because it's the type of motor that was on the mini mills when they were first introduced around 1995 or 96, somewhere in that time frame. And later on, a new type of motor was introduced, which is called the brushless DC motor. And let's move over to another mill and take a look at that. Here I have the mill I use for most of my operations in my own shop. When I'm working with the mini mill, at least. I also have a larger mill over on the other side here. But this one is the model 3960 from littlemachineshop.com. And it's also manufactured by SIEG, but it's sold under the littlemachineshop.com brand name. And this one has the brushless DC motor. And the brushless DC motor has a few advantages. One is that it's got quite a lot more torque for its size, and consequently you can see it's only about half as tall as the other motor that we just looked at, but it actually has more torque than the other one. It also is completely sealed from dirt and grit and oil or any contaminants that might get in there, which should lead to a very high reliability and long life. And it doesn't have any brushes to wear down, so there's virtually no maintenance required on it. It's also a lot quieter and direct belt drive because it has a very high torque capability. It doesn't need the internal high-low gears to attain the necessary torque for heavy-duty milling. And so you get several advantages. So you have a direct belt drive here, and that also means that it runs quieter. So we turn this one on. You may notice, if you're paying attention, it's really a lot quieter than the other one. It's more like a sewing machine. So if you are looking for a top-of-the-line mill, that's a feature you want to look for. And in fact, there to my knowledge, only 2 vendors in the U.S. who sell these. LittleMachineShop.com is one, and they sell at least 2 different models of mills that have this brushless DC motor. And the other one is Micromark, sells a very similar mill. But the other mini mills sold by Harbor Freight and by Grizzly and other vendors in the U.S. have the classic style brush type DC motor. Something to keep in mind if you're comparing prices. The brushless motors are going to be quite a lot more expensive generally than the brush type, but keep in mind that you are getting some significant benefits for those extra dollars. Although the mini mill makes a pretty nice drill press in many respects, one way it is limited is that it has a fairly short headroom, and the headroom is basically the distance between the table and the maximum height of the spindle, which measuring here from the table is about a little over maybe 11¼ inches or 11 and maybe 11½ at the most, which is pretty limited. As you can see with the head all the way up here, I've only got about 5 inches, maybe 5¼ inches from the top of my workpiece to the bottom of the chuck. So if I were to use a fairly large diameter drill bit, let's take this 1/2 inch diameter drill bit and stick it in here. You can see it's barely enough room to get it in there. So that is a limitation of the mini mill compared, for example, to a larger mill or a drill press you need to be aware of. Now, I mentioned earlier that this uses an R8 spindle, which is the designation for the type of spindle taper. There is one version of the mini mill sold by Grizzly, which uses a different Morse taper spindle. It's a Morse taper number 3 spindle, and a potential advantage of that is that this part of the spindle is about 1 inch shorter, so you gain almost 1 inch of headroom, or the spacing between the spindle and the table. That can sometimes be an advantage when you're in a tight spot like this. Another way to deal with this limited headspace or limited headroom is to use shorter drill bits. And I have here a set of drill bits. They're conventional, but they're referred to as screw machine drills, and they are short and stubby. So if you don't need to drill a very deep hole, you can use one of these shorter drill bits and gain about 1.5 inches, it looks like, maybe almost 2 inches compared to a standard so-called jobber size drill, maybe even more than that. So these short drills are also handy on the mini lathe, where the shortness of the lathe often is a problem when you're trying to work with a relatively long workpiece and a relatively large diameter drill. I've found quite a few situations where these short stubby drills save the day by letting me fit the drill in there where a standard jobber length drill would not fit. Well, while we're on the subject of drill bits, let's take a look at some of the options you have for the mini mill. This is a classic set of inch drills from 1/16 of an inch all the way up to 1/2 inch in increments of a 1/64 of an inch. And these sets are available all over the place under different brand names and different designations for length and so forth. But they typically have 29 drills, and they range in price anywhere from $30, up to maybe $200 or $300 for a top quality industrial type set. And the high-end ones are in fact very nice to use if you can afford them. But for most of us who are hobbyists and are very limited on our budgets, we have to make some compromises and trade off a little bit on the quality end to get stuff that we can actually afford. This is a set of drills sold by Harbor Freight, and it has a set of number drills from 1 to 60, which are real nice because they give you a lot of smaller sizes and fill in a lot of the gaps that the standard inch sets don't have. And then you have your inch drills, same as the set we just looked at, your 29-inch drills from a 1/16 up to a 1/2 inch by 1/64. Then you also have this third section here, which are the so-called letter drills. And the letter drills span a lot of the same dimensions as the inch drills, but they have diameters that are often in between the gaps on the inch drills. And if you're trying to drill a hole of a certain size for which an inch drill isn't available, you may find a letter drill that is just the right size or closer to it than the nearest inch drill. So those are some of the choices, and you can buy the letter drills and the inch drills and the number drills in separate sets. So this is a set of number drills sold separately, and here's a similar set, I think probably from Harbor Freight, and they're pretty good. They're not as good as this old American-made set by Morse. These are top quality drills I bought back in the 70s when I had my first lathe, but they get the job done, and for accuracy purposes they're generally close enough for the type of work I do anyway. And if I need more accuracy, I usually reserve my old American-made drills for when I really need them. I mentioned early in the video that the mini mill was great for accurately positioning holes, and if you're going to do work where you might need to lay out, for example, 4 holes or 5 holes or 6 holes in some sort of pattern where the holes are very accurately spaced and maybe accurately positioned with respect to an edge or some other feature, then you have to take more care and do some preparation work to make sure everything comes out where it's supposed to. So in this case I have a little chunk of aluminum here, and let's just say we wanted to drill 4 holes that were evenly spaced or spaced to some specific measurement. Now typically the way you would do that is do what is called some layout work on a surface plate. And a surface plate, if you're not familiar, is a heavy slab of granite that's precision ground. And if I put a dial indicator on here and run it across this surface, you'll see that there's essentially no movement at all of the dial, or very, very little. And these are typically, even in the lower grade ones that are intended for hobbyist use or low grade industrial work, these are typically flat to a 10,000th of an inch across their surface. And of course you can buy much higher quality ones that have even greater precision. But these low cost ones are fine for most of the work we're going to do in the hobby shops. And they can be purchased from anywhere from $30 to $100 typically. This one I think is about a $50 one on Grizzly, but they're heavy. They're made from solid granite, and they typically weigh 70 pounds, and the shipping on them often can be more than the cost of the surface plate itself. So if you're in a place where you can drive to Grizzly and pick one up, throw it in the trunk of your car or your pickup truck, you'll save a lot of money on the shipping. Or if you watch carefully, every once in a while Grizzly and other vendors have a specials deals where you can get free shipping for some period of time. And that's a great day to buy a surface plate if they'll let you ship it for free on one of those deals. But let's take a look at how this is used if you're not familiar with it. Well, the first step in laying out a piece of work here is you want to coat it with a thin layer of layout dye, and the traditional type of material used for that is something called Dychem or similar product, which is a deep blue or sometimes red dye which coats the surface of the material and is pretty quick drying. But I have this little fan here on my surface plate, and that speeds up the drying process even more. Now if you're doing really careful work, you want to make sure you always keep your surface plate clean, because if you get any grit or contaminants on the surface plate, they can throw off the accuracy of your measurements. And you can tell just by running your hand across here if there's any grit or anything else sticking up from the surface. Your hand is actually surprisingly sensitive to that. Even if it's just 1,000th of an inch or so, you can usually detect little pieces of grit. But I clean mine periodically with some alcohol, rubbing alcohol or denatured alcohol on a gun cleaning patch is what I use. And different people have other preferences for that, but that's what I use, and it seems to work fine for me. So now our dye is dry, and we want to lay out our holes. So I'll turn the fan off. Now the whole premise of a surface plate is that you have a flat reference surface that you can use, but that only is of much benefit if the edges of your workpiece are also correspondingly flat, or at least flat to whatever tolerance you need to maintain within your work. And on this particular workpiece, I have one rough edge here that was just cut off on the bandsaw. And if I were to position that on the surface plate, you can see it's kind of wobbly because it's not flat at all. And by contrast, if I put it on one of the machined edges, it will stabilize more quickly, hopefully, because they're flat. And you can determine the flatness and whether there's any. You could take a precision 1, 2, 3 block like this, or a precision square, and bring it up to your work. And you can tell just by eyeballing that whether it is in fact square or out of square. And of course this rough edge here is not square, but I'm going to ignore that for the moment. What we'll need to do is stick this in the milling vise and mill this edge square in order to get an accurate layout on this piece. Well, my other mini mill is already set up with a milling tool and pretty much ready to go, so I'm going to use that to clean up that edge, and then we'll be ready to go ahead and mark our layout lines. So we'll fire up the mill here, just touch off on that edge, and I'll just run it along there and get that rough surface off. Didn't quite get all of it, so I'm going to come back, and this is called climb milling when you're coming back the other way, and it actually does a cleaner job generally than conventional milling, which was cutting into the tool. But you have to be careful when you're doing climb milling because it can draw the work back and cause some vibration and other problems. But we got the job done that we needed to do. Often in the process of milling, you'll leave little burrs along the edge here that can throw your measurements off, and in order to avoid that, I'm just going to touch it up here on this disc sander. And that just cleans any burrs off, so I'll get an accurate alignment. Now to mark our lines where we want to drill our holes, I'm going to use a digital height gauge, or a height gauge. This one happens to be a dial type, and it uses a gearing system. And I used this for many years, but nowadays you can buy the digital type at somewhat reasonable prices. They're still expensive. This one, I think, was from Harbor Freight. It was probably around $50 or some dollars, $55 or something like that. But the digital ones are a lot nicer to use. They're real easy to zero, and they don't have the problem that the gear type ones have sometimes of getting grit in the gears. Since they don't have any gears, that's not an issue. The only problem I have with this one is it's a little bit difficult to read, and particularly you can get parallax, or just makes it it's very hard to read sometimes without tilting it back. But aside from that, it's a nice little unit, and it does everything I need. So let's just say arbitrarily here that we're going to set this to a 1/2 inch height, so I'll switch to inch units, and then I zeroed it to the surface of the surface plate. I'm going to bring it up here till I get it close to a 1/2 inch, about there, lock it down. I'm going to lock this upper thing, and I'll drop it down and use this fine adjustment control to bring it to 500. There we go. And now I'm just going to scribe 4 lines. 1, 2, 3, and 4. And that just gives me a little square or rectangle there, and we're going to drill holes at the 4 intersections. So in actual practice, there would probably be some other dimensions involved, but this is just an illustration to show you how to use the height gauge and the surface plate to mark your layout lines for, I'll call it a precision drilling operation, although it may not depending on your definition of precision, you may or may not agree that it's precision, but it will probably be, the holes will probably be accurate to plus or minus 5 thousandths in the X and Y axes, and maybe a little better if I'm lucky. I've moved my workpiece over here into the vise, and if I wanted to do truly precise work, I would use an edge finder and probably a digital readout or some other precise way of measuring the table movement in order to position the drill or the spindle directly over these reference marks. But for the purposes of this demonstration, I'm not going to go to that level of detail. And what I'm going to do instead is just mount in the drill chuck a sharply pointed tool that happens to be highly concentric. And this is a little tool that you can get these sets sometimes of small carbide drill bits. You can sometimes find these on the internet or from Harbor Freight and places like that. And often within those sets you'll find just a little sharp pointed tool that happens to have a precision ground shank on it. And that's where I got this, and it's handy for operations like this one where we want to line up the drill bit with a reference mark on the workpiece. And if I'm trying to get this as accurate as possible, I'll usually use my magnifying headgear so I can look down here and see exactly where that thing is pointing. Let me do that. This magnifying headgear that I'm going to put on, and then I'll look through that, and that gives me a much better view or closer view of exactly where the tool is pointing, and I should be able to get a pretty good alignment that way. Okay, so we've got it lined up pretty accurately now, and we'll raise the head up a little bit here and take that pointer out because it's just used to do this lineup work, and then we'll put a small center drill in place. Let's haven't really decided what size hole I want to drill because this is just a demonstration, but we'll pick a number 2 center drill here and get that put in the chuck. And put a few drops of cutting fluid, in this case Tap Magic aluminum, over our hole. Okay, and there we have our pilot hole drilled. And this is where the rack and pinion dovetail vertical column is nice because I can raise the chuck up out of the way so that I can get a drill bit in place. And let me just pick a drill bit here. And in this case I'll use a 1/8 inch drill. Well, we'll go with a 5/32, and I'll put that in the chuck and tighten it up. And I've chosen to use one of my short stubby drills, my screw machine from my screw machine drill set, and that gives me a little bit more clearance. And all else being equal, we'll have less flex in that drill, and should give me, you know, a nice clean hole without any bending of the drill bit. Okay, now here again, if I had a digital readout mounted on this mill, I could just set my 0 point and then move to the next hole and the next hole, and would get very, very accurate registration. But this particular mill does not have a digital readout, so I could use the dials on the table, but they're a little cumbersome because you have to pay close attention to the indications on here, and you have to count how many full turns of the handle you make as you're moving along. But another way you can do this is you can set up a dial indicator. There are 2-inch dial indicators, and for small work like this you can often clamp a dial indicator so that it registers up against the side of the vise, and use that to accurately position between the holes. But for work like this, just visually aligning on each crosshair, as we did for the first one, is good enough. So that's what I would do. I'm not going to repeat the process because it's pretty much the same for each hole, but I think you could see how you go about laying out and drilling a series of holes that need to be positioned with accuracy with respect to each other, perhaps to other features such as the edge of the workpiece.